race car battery cooling simulation. So let's do this first, okay? Shall we? And afterwards we turn to the helicopter and connect to this simulation. While it's still loading. Oh, it's up. Okay. Here we go. Of course you can't see. I need to reposition my camera. I'm sorry. Oh no, I didn't. Did I? Okay, I need to reposition my camera. Where is my camera? Here's my camera. Because otherwise you can't see the color bars. Yes, that perfectly fits, I guess. Okay, so let's get into it. This is our race car. This is also another simulation that was not done by myself. This was done by a Formula student team. They are designing race cars, electric race cars in that case, with several teams. And these race cars are, they have a dry weight of like 170 kilograms and are limited by the rules to 80 kilowatts. So they make it to 100 kilometers per hour, 60 miles per hour, in less than 3 seconds. And that's really, really fast. You can have multi-G cornering in them, and they have very, very refined aerodynamics. And I'm very proud to say that a lot of these teams use my product, Simcenter STAR-CCM Plus, to optimize their aerodynamics. The Aachen team, Écurie, they also used it for their battery cooling. And here we can see the battery. I have cut away some parts of the body of the car so we can look inside. And there's also a part of the accumulator missing. But we can also see everything from here. We can see like the main switches, the main connectors, some electronics. There is a plug for connecting the battery. Down here there's a plug for connecting the battery to the car, or to the charger when it's outside, because the whole container can be dragged out to the end. And yeah, there are some safety features we can see. There are battery management PCBs, so these printed circuit boards are for battery management. We can see a whole lot of electronics down here. Yes, which I don't understand anything from. Besides, that's very neatly packed and very nice routing in CAD. So here we stand atop of the accumulator container. On the left side we can see the solid accumulator. On the right side it's cut away, so we can look inside. We have a temperature scale saying 30 degrees to 60 degrees. 60 degrees is the limitation by the rules and most likely harmful to accumulators if exposed over longer time. So we can see here on the left side there are some palish blue colors on the on the PCBs on top. That's plastic. It's not very hot. We can see these rose colors on the on these cooling bodies or heat sinks. And yeah, that's like the interface between the the cells below and the air, and this is conducting the heat out. And we can see in solid pink below the accumulator cells. So these are the cells actually. They are modeled as a solid with a heat source, but they have also like a one-dimensional function behind that's also modeled. Yeah, and with this we can simulate our cooling of the accumulator. We have some inlet up front here, and we have some fans at the far upper end. Yeah, and then some outlets. So the fans are not shown actually here. Right. So what we can do, of course, is we can visualize not only like the surface temperatures, but we can also visualize the flow in here. Come on. Okay, I guess my bubbles are, just because I'm so small, they are way too fast. Yeah, so let's tune them down. Yeah, we can see them now and then. Making them slower, come on. Oh yes, there we go. We need them slower, 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 slower. Come on, slow down. See, you can like infinitely tune them up to speeds. So, here we go. Making them a little bit bigger as well and slower. Okay, and we can also like, if they spawn between these fins, you can see that they get blocked and slowed down. The colors, in this case on the bubbles, do not mean temperature. Here you can see, on my right side, you can see that this is velocity of the air that's speeding along. Ah, and there was a preset spawn as well. See? These bubbles follow the airflow from the inlet down to the outlet. And they carry along some temperature with it. This way you can optimize your cooling route your for less flow resistance or equal airstream distribution. So you have lower temperatures in your accumulator container. From that view only, looking at the surface temperatures, one might think that the outside is not perfectly cooled, but the middle of the container is better cooled, because outside the PCBs, the plastics on top, are reddish. They are nearly pink, yeah, which means high temperature from our scale. And in the middle, they are bluish. But batteries don't care for surface temperatures. They don't even care for average temperatures. They care for hotspots. So let's see what we can find in here. In here we can make a plain section like this. And there we can see, okay, temperatures from 59 to nearly 60 degrees. Yeah? And with this cut section, and we can also see that the heat and the temperature in the heat sinks is fairly below these temperatures down here. Okay? Okay. Yeah, I can quite intuitively place these sections around here. But that's not the best way to find a hotspot. The best way to find a hotspot is using isosurfaces, because I can literally just take the same, see, the same scale as I have down here is up there, and I can go and try to find the... it's a bit difficult because it tends to hop back. And here we go. That is our hotspot. Yeah, these are the hottest zones of the accumulator. And it's, to be fair, to my eye, that is nearly evenly distributed. Of course, it's a bit less volume at the front. Yeah, because the cool air is coming in from the front and going to the back, right? But left, right, middle, the outside is even a bit less hot spottish or something. Yeah, just because you can also cool to the sides. Yeah, obviously you lose some temperature there, and in the middle it's a bit better, but it's so equal. To be fair, especially for the student team, I need to say that I have tweaked the color bar. Yeah, you can see if I do this, the yellow part is that's like half a degree or something, not even maybe. Yeah, I have tweaked the color bar because there's nothing as boring as a good cooling simulation. Yeah, it's all equal, and you really have to try hard to find these hotspots. And that's what my boss also told me. With this simulation, he is totally convinced of the use of for VR for CFD, because finding that hotspot, yeah, like swiping through here with a plane section, yeah, making some ISO surfaces here and there to find the hotspots, that's so much easier than trying to type in some numerical values while sitting in front of a screen. Yeah, or try to swipe through there with your mouse and your keyboard. It doesn't work. Yeah, that's just easier in VR. Yeah, you can natively rotate that plane section. It feels like the way it should be. Right? Okay, cool. Let's see what the chat does. It takes a lot of hardware. Hi PinSimul. Thank you for chatting for the very first time. It takes a lot of hardware, yes and no. It doesn't take more hardware than you need for simulating anyway. It takes a decent GPU to display this. It's a 3080 Ti, if you're familiar with that. And yeah, that's how it works. You need some hardware. Hardware costs are so much less than the total cost of employing engineers. Yeah? So, please excuse me, I will now shut off my camera because I want to record this fly through for the race car without myself in it. Okay? See you in a minute. I can still talk though, and you can still hear me because the sound will not be recorded anyway. So let's get these cones away. What's wrong? Okay. Okay, let's start outside again. And we will remove the ISO surface here as well. So maybe we start over at the other side of the race car, because from here you can't even see what's going on. So we have a wonderful racetrack. We turn around, and there we have a race car. Can fly around. And take a look at the accumulator container. And then we can get closer, and we can get smaller. until we reach that state here, where we have different temperatures on the surfaces. So let's get as close as we can, and let's do some bubbles here. With these bubbles we can visualize our flow speed, or velocity better to say, because they are just like streamlines. They just follow the vector field. It's like an integration. So let's see, I can also clip this away if I want to. And I can dive deeply down here. And here I can make a plane section. Take a look at it from above. So happy that you don't see how follically challenged I am, because I turned my camera off. Let's remove that plane section. And let's go for some isosurface. The blue one only covering the air above. And the hot spots, the hotter it gets, the smaller the volume becomes, and it only shrinks down to the hot spots, which in fact are like these two here. So let's make a plane section through there. And we can see where the hot spots are. Okay, I guess that's it. Let's fly out, back again.